Hi there. We are continuing with the parallel connection, but this time we're going to perform some algebra. We have our circuit with 4 resistors, and we also have a source voltage. Whether you name it source voltage or voltage source doesn't make really a difference in our case. The resistors are labeled here. We have 70 ohms, 100 ohms, 80 ohms, and 270 ohms, and the source voltage is 120 volts. And our goal is to compute the currents that flow through each individual resistor, as well as the total current. Later on, we will be computing the equivalent resistance of the whole circuit and also the electric power. Let's get started with the individual currents. The formula is listed here, and to apply it to our example, we're gonna state US, the source voltage, divided by R1, and that's equal to 120 volts divided by 70 ohms, and that's equal to 1.71 amps. And doing that for the other resistors is now quite simple, since we have to follow the same routine. So 120 volts divided by 100 ohms, that can be done in the head, and that gives us 1.2 amps. I3 R3 is 80 ohms, and that gives us a nice number. For I4, by the way, you have noticed that I accidentally put I2 here, so I'm gonna erase that. Oops. Well, that was a temptation to literally copy and paste, but you have to pay attention to the subscripts, so don't entirely copy the subscripts. And this one is 270 ohms, so it's not going to be that easy any longer to compute the value in the head. And that gives us 0.44 amps. So these are the individual currents flowing across each resistor. And as you can remember from the previous video, computing the total current from the individual currents requires us to add them up. (1.71 amps plus 1.2 plus 1.5. You better put the unit behind each number because you need to stay physically consistent. If you leave out the unit, you might get points taken off on your exam or your homework. And the sum of all individual currents is 4.85 amps or ampere. So that's your total current. Total current drawn from the voltage source. And now we want to compute the equivalent resistance, or the total resistance of the whole parallel connection. In the previous video, you saw two different formulas. In one formula, you had R dot directly written, and in the other formula, you had R dot as an inverse. For convenience, I'm going to use the formula with the inverse because that formula is more common in physics, in literature related to physics or engineering studies. So let me shift it to the left a little bit. So the formula is 1 over R dot, the total resistance, and that's equal to the sum of the inverses of the individual resistors. And in our case, summing up the inverses would gives us 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. And you may have noticed that sometimes I said resistors and sometimes resistances. So to clarify, a resistor is the electrical component. A resistance is the value, well, is a resistance. So the number of ohms. And now I'm gonna plug in the numbers. By the way, I'm gonna show you something that you don't wanna do because that is wrong. Some students, including myself, back in my days, I was tempted to do this because it was so convenient, but it's mathematically wrong. So don't do the following. I'm gonna actually use a black color to indicate that you don't want to do this. So don't do the following. So don't do this. If you had a product here instead of a sum, you could do this because then you could simply put all your values into the denominator, but don't do that here. Okay, so that's a no-go. I'm mentioning this because some students are tempted to simplify it this way because obviously it makes things so much more simple, but you don't want to do that, as I said. Instead, you have to compute each of the fractions separately. So 1 over 70 ohms plus 1 over 100 ohms, and writing down the value into the denominator first makes sense because that way you can estimate how much space you need for your horizontal bar. Okay, so adding up these values gives us 1 over 24.7 ohm. And since this whole thing is an inverse, so we have computed not the total resistance, but the inverse of the total resistance. That means that the value of the total resistance is equal to 24.7 ohms. Okay, so don't forget to add these fractions and then to take the inverse of your result. Of course, you could use the other formula that I have stated in the previous video. That way you can compute your R-tot directly without taking the inverse. But as I said, the mathematical result should be identical. It's just that if you use the other formula, you have some more inverses, which again yields the same result in the end. Now, here's one useful information for you. The way to compute the total resistance is either to apply this equation that I have just shown, or what you could also do, you could use the equation related to Ohm's law and rearrange this equation into R, which would be R is equal to U divided by I. So U is your source voltage of 120 volts, and I is your total current in the circuit, which is 4.85 amps. And if you divided 120 volts by 4.85 amps, you would obtain the same total resistance as you see here. You may have a little different numbers as your final decimal because that's a rounding issue, but if you do it precisely, you should obtain the same value. So if you have computed your resistances and your currents and your total current, you can also calculate your total resistance by simply dividing the voltage by the total current. And now, at last, I'm gonna compute the electric power. I'm gonna use a different color for it because you can see a lot of blue here, so I'm gonna use orange to make it stand out against the rest. The electric power is the product of voltage and current. In our case, it's the source voltage times the total current. And by the way, we're looking for the electric power of the whole circuit. That's equal to 120 volts times 4.85 amps, and that is equal to 583.2 watt. So that's how you perform the math on parallel circuits, and all I hope is that it was helpful to you and that you have now more confidence in approaching the mathematical calculations with these connections. Again, I thank you for watching, and I would be happy to have you back with us.